Is it running now? Yeah. Okay, thank you. All right, so we've come a long way. So just by looking at this vector potential being written in terms of the photon creation radiation operator, we could look at the Hamiltonian of the point particle. And in particular, we looked at the case of the hydrogen-like atoms, where potential is given by this. We expanded this piece of the Hamiltonian out. This is the zero-polar Hamiltonian, and the perturbation of the system was given by this. And what we could do already at this stage was looking at the fact that this A contains creation and annihilation operator of the photons. We could compute the process of 2p state decaying to 1s state by emitting the photon. And we don't actually keep using this, but it turns out that the most interesting examples you would like to understand in the basics of quantum mechanics appears typically at the second order perturbation theory. And what we did so far is I hate this noise. It needs to be lubricated. We got the Fermi Golden rule. And this was really useful when we discussed this 2p state of the hydrogen atom decaying to 1s state by emitting a photon. But suppose you want to study a process that you have an atom, you send in a photon, and that can scatter. So in this case, what you have to do then is that you annihilate this photon, and you create that photon, right? That's how you can describe the scattering process. And that can happen with the second term of the Hamiltonian, because it has a squared in it. You can annihilate one photon initial state using one power of the vector potential. You can create the final state photon using the other the power of the vector potential. So this can happen already at the first order perturbation theory, but it turns out that if you do that, you don't get the right answer. And that's because you can also use the first term in delta H twice. You can use delta H first time to annihilate this photon, and you can use that Hamiltonian once again to create the final photon. Then you're talking about the piece that goes at the second order perturbation theory. So we at least need a formalism where you generalize the previous golden rule, not at the first power in delta H, but also at the second power in delta H. The way you would do that is in quantum mechanics textbooks called time-dependent perturbation theory. Dependent perturbation. And Fermi's golden rule turns out to be just the lowest order expression for that. Then now I have a question for you. So time-dependent perturbation theory comes with interaction picture, with a type of evolution operator which is given in terms of what is called time order product. Have you seen this in quantum mechanics? Some of you are nodding. Everybody? Not everybody, it seems to me. You haven't. Well, it may depend on the instructor, so in that case, I have to just go through this. So the idea is that we would like to develop perturbation theory in a way that you can describe this kind of transitions, namely initial state goes to some other final state, and therefore it's a time-dependent process. And you would like to compute the rate of transition, just like the Fermi's golden rule at the lowest order perturbation theory. And in order to do so, I think it's Dirac that invented the idea called interaction picture. So what is the picture? When we say picture, normally we think of some pretty picture. And in this case, we're talking about the definition of state and operators. And most of the things you have done in 137, I believe, is ensuring a picture where states evolve. So if you have a cat at time t, this is evolved from the same cat at time 0 by the time evolution operator, which is the exponential of the Hamiltonian. And you can immediately see this is the solution of the Schrödinger equation, at least formally, because if you add IH bar ddt on the state, time derivative would pull out exponent, so that it would give you the Hamiltonian. And that's the Schrödinger equation, right? So the Schrödinger picture has this time-dependent state, which satisfies the Schrödinger equation. And the formal solution of the Schrödinger equation is obtained just by exponentiating this Hamiltonian operator. And this is a time evolution operator. So that's something you have seen. And in this picture, operators don't depend on time. But there's another picture called Heisenberg picture, which is physically equivalent, because in either picture, when you compute, for example, expectation value of an operator, and if you try to do this in Schrödinger picture, what you would do is the state depends on time, operator doesn't depend on time, and end result, of course, is a function of t. So you're computing some expectation value of an observable changing as a function of time, so that's what you would do in Schrödinger picture. But you can also try to do it this way. Namely, the state doesn't change, but what changes the function of time is the operator to capture the same physics. And that is the picture called the Heisenberg picture. So in this picture, state doesn't change. But in order to keep the expectation value the same, I can go back to this expression in Schrödinger picture. We now know psi t is psi 0 with the time evolution operator. So this thing is psi t in Schrödinger picture. And then I have operator. Then I have the Hermitian conjugate of this whole thing. And when you take a Hermitian conjugate, you have to be sure that you change the sign of I. So now you can see that the connection between the Schrödinger picture and the Heisenberg picture is that this psi 0 is nothing but the psi in Heisenberg picture. And this time evolved operator is the definition of the operator in the Heisenberg picture. So now what we have is that OT is expressed using time evolution operator in this fashion. So showing a picture and Heisenberg picture give you exactly the same physics. Expectation value of the physical observables come out the same way by design, but you can do it either way. So that's the difference of the pictures. So the word picture in this case is meant to be the way you look at things, hence the picture. Namely that when you look at something changes over time, you can look at it in a way that you attribute time dependencies to the states by keeping the operator the constant. Or you can look at the same physics by keeping the state unchanged, but it is the operator that is changing over time. And either picture would give you identical results of physical observables. So that's the idea of pictures. And now that operator depends on time, you can also work out time dependence of the operator just by differentiating this expression. H by ddt, if this operator hits this one, that pulls out Hamiltonian in the same way we did that for the Schrödinger picture. So that's O H. But time derivatives can also hit this one over here. Then pulls out IH over H bar times IH bar. So that gives you negative Hamiltonian. So I get negative Hamiltonian operator. So that combined together becomes this commutator. And this is what we call the Heisenberg equation of motion. And Heisenberg equation of motion looks pretty much the same as a classical equation of motion. For example, if you put in x there, and Hamiltonian is that of the free particle, then time derivative of x operator, position operator, is given by xh, and x doesn't commute with p, the commutator is IH bar, but you have t twice, that cancels a factor of 2, so you end up getting this. And if you remove IH bar from both sides, you find time derivative of x, namely the velocity, is given by momentum over m. So P is mv, that's what you know from classical mechanics. But this is meant to be an equation among operators, position operator that depends on time, momentum operator that depends on time, and they satisfy this equation, which looks very much the same as a classical equation of motion. So this is the Heisenberg equation of motion. So the idea so far is that you can have these two different pictures, showing a picture which we normally use in quantum mechanics class, and then you solve the Schrödinger equation to find the time evolution of physics. You can also do it in the Heisenberg picture. In this case, state doesn't change, but operators obey Heisenberg equation of motion. And if you extend this to, for example, harmonic oscillator, this is still the same, but you can also derive Heisenberg equation of motion for the momentum operator, which turns into this. That's the Hooke's law of a spring, right? This is the time dependence of the momentum, so that's MA, because this is P is MP, and time derivative, that's NA, X double dot, which is given by the force. So this is the F equal MA in classical mechanics. And you derive the same equation of motion for the position of the particle, just like in classical mechanics. But in this case, X is now an operator instead of a number. So that's something you can derive in Heisenberg equation of motion. And we will come back to Heisenberg equation of motion later on, because when you go to relativity, I emphasize this at the very first day of this class, that when you go to relativity, you would like to treat space and time on equal footing. We are doing field theory. Fields depend on possession. But in showing a picture, field is an operator, so that doesn't depend on time. So field depends on space, but not on time. And you're not treating space and time on equal footing. When you go to relativity, Heisenberg picture is much more natural thing to do, because then the field operator depends on time, in addition to the dependence on possession or space, by definition being a field. Then you're treating field operator as a function of both space and time, and then you're treating space and time on equal footing. So the Heisenberg picture is actually the preferred choice in relativistic QFT. So we will talk about that when we talk about the relativistic QFT, which is written on my t-shirt. This is a Lagrangian or relativistic quantum field theory, so we'll come back and talk about this. But the purpose of discussion here is to develop this time-dependent perturbation theory, and that's when Dirac came up with this clever idea. That you can come up with a third picture called interaction picture. And that's sort of halfway in between Schrödinger picture and Heisenberg picture. And basic idea is the following. When you talk about operators, and because we're talking about perturbation theory, you're separating your Hamiltonian into two pieces, zeroth order Hamiltonian and the perturbation of the system. And zeroth order Hamiltonian is something you know how to solve. So you know how to solve the Heisenberg problem. You know how to solve the harmonic oscillator problem. So you pick zeroth order Hamiltonian so that you can solve the problem. Then you know exactly how operators change as a function of time. So you introduce time dependence on operator according to the zeroth order Hamiltonian. So this is a zeroth order Hamiltonian. Then the state evolves according to some time evolution operator, which is neither H0 or full Hamiltonian, somewhere in between. And now that we are separating this time evolution operator for the piece how you can solve the problem, and just pretend for now that you can ignore the fact that operators don't commute in general, and think of this as just a sum of the two. And this is where I pretend that I don't have to worry about commutations between operators. And this is, of course, questionable. But just to get the idea, if you attribute this time evolution according to the zeroth order Hamiltonian to operators, then the remaining time evolution is only due to the perturbation of the system. So then operators evolve according to the free Hamiltonian, the zeroth order Hamiltonian. But then you can see that this time evolution of the states is now only due to delta H. So then you can separate the roles of two pieces, namely the zeroth order Hamiltonian that's responsible for the time dependence of the operators, versus the time dependence of states that is only due to the perturbation of the system. And then you have separated these two pieces, in one attributed operator, the other attributed state. And this actually turns out to be a very good way of developing perturbation theory. But of course here, I ignore the fact that delta H and H naught may commute with each other. We have looked at this, what is it called? Baker, Campbell, Hausdorff formula. So when you separate these two exponents, then you end up having a bunch of these commutators in addition to it. So this is clearly wrong. We have to do it more correctly. But at least you get the idea what we are trying to do in this picture. It was called the interaction picture. So what we would like to do is to develop how we can compute UI without neglecting commutators, so that we can capture the information on a perturbation, the perturbation Hamiltonian in a time evolution of states. So that's the thing we need to do. And once we have done so, then you can systematically compute this time evolution of states at any order in perturbation theory, and then you can apply that to a problem like the scattering of light by an atom. So that's the goal. Okay, any questions where we're going? Alessandro?
In this case, delta H is 0 at t equals 0, right?
Delta H is 0 at t equals 0. So what you're saying is that UI of 0 is 1.
Exactly.
Yes.
This is true. So basically, when we have time-independent perturbation theory, this is just H0.
Well, so that at time 0, of course, everything is frozen at time 0. This is also the same as this one.
No, what I'm saying is that if the perturbation theory is time-independent,
yes,
then H0 includes also the perturbation, right?
No, H0 doesn't. So
but if the perturbation is time-independent.
Sorry?
If the perturbation is time-independent.
Yes.
Where do I have to put that?
So I think that becomes clear when we actually start to write things down.
Okay.
Any other questions where we're going? And those of you who have seen this, of course, are not learning anything new, but hopefully it's at least a good reminder to refresh your memory about this. So clearly, key object to look at in this interaction picture is this time evolution operator due to the perturbation of the system. So we'd like to work out UI. But before doing anything, actually you know what UI is, because what I have done, again, is to keep this expectation value the same in all pictures. In showing a picture, this is due to time dependence of the state. And we know time dependence of the state is given by this time evolution operator for the full Hamiltonian. In Heisenberg picture, it is the operator that depends on time. The state doesn't change. But by definition, it is supposed to give you the same answer because the operators depend on time. Again, using this full Hamiltonian. So they are clearly the same. So that's how we design in a way to go from one picture to another. And now what we like to do in interaction picture is this is the state that depends on time in the interaction picture. Here's the operator that also depends on time in the interaction picture. And because this is just a change among pictures, this is supposed to be the same as what you get in other pictures. But we demanded that operators change according to the zeroth order Hamiltonian. So this is e to the I H naught So this is the definition of the time-dependent operator in the interaction picture with subscript capital I. I just wrote down the definition of it according to that table over here. And to make sure that this is the same as that one, you know that this thing has to be the same as that one, right? Then you are guaranteed that again, observables come out the same way. So by solving this equation, by acting inverse of this operator on both sides of the equation, now you find the definition of the state in the interaction picture. So this is a state that does depend on time in the interaction picture, which is related to the state at time 0. And now you have the product of two time evolution operators. First one, depending on full Hamiltonian. Second one, depends only on a zero-order Hamiltonian. But again, if you pretend that they commute, then you just add exponents. And what you find is that if you add exponents, h minus h naught appears here. That's nothing but the perturbation delta h. So you see that this time evolution is only due to the perturbation of the system. So in some sense, this is trivial. You just multiply them together. But what is non-trivial is that you know how to solve the problem with the h naught, but you don't necessarily know how to solve the problem with the h. So typically, this operator is complicated, and you can't work it out exactly. So what you would like to do is to write this combination in power series expansion in delta h. Then at each order perturbation theory, at each power delta h, you are only dealing with operators that depend on h naught, which you know how to solve. Then doing the perturbation theory according to delta h to some arbitrary powers in expansion, and then you can start computing things. So this is the UI, which I brought in here, namely how the states in an interaction picture is evolved from the state at the z time 0. So this UI is a time evolution operator in an interaction picture. And we know, at least formally, can be written down this way, using zero-order Hamiltonian and full Hamiltonian. We already know that in the absence of perturbation, when h naught and h are the same, this is just one and trivial. So it really does disappear when you don't add the perturbation to the system. But right now, it's not written in a convenient way because it doesn't show you power series expansion in delta h. So we try to come up with the expansion. How you write this time evolution operator in power series in delta h. And so that's the next thing we need to do. So the goal, once again, is to separate the role of the zero-order Hamiltonian in a perturbation of the system. So that's the idea of interaction picture. If you do so, time evolution operator is something you know how to do because you know how to solve the problem with the zero-order Hamiltonian, like the hydrogen atom or harmonic oscillator. This you know how to do. What you don't know is to deal with this time evolution of the state. And formally, this time evolution of the state can be expressed by the product of two time evolution operators. So you know what it is, but you can't quite work out this time evolution according to full Hamiltonian, which is a complicated problem. But because we know this product just reduces to 1 in the absence of perturbation, we know we should be able to expand this in power series in perturbation Hamiltonian, and that's what we would like to do next. And once you have done so, then you can apply this time evolution operator for any system you like, time dependent. So you can use this time evolution operator to compute transition processes that initial state of your interest somehow evolves into final states of your interest by just sandwiching this time evolution operator between the initial state and the final state. And that's how you can use this time evolution operator in the interaction picture to develop calculations in power series in delta H. Okay, so that's what we like to do. Any questions about what we're trying to do? Okay.
So I understand that the reason, because we wanted to separate the perturbation from the H naught, which made us want to have both the operators and states to be time dependent. But I'm thinking of I'm thinking about the meaning of the operators now, because now if I have the operators being dependent on t and only dependent on the H naught, so it means that the operator can only be affected by the zeroth or first order. It's H naught.
H naught, that's
H
right.
naught.
Yeah.
Which means that it is the, how to say, is it ordinary or the most fundamental level of energy from the operator? Because I'm trying to translate the meaning for the operator.
So let's see. I'm not sure I fully understand the question.
Sorry.
So you were trying to get some intuition
Yes.
on
Yes,
what these operators do, right? Yeah. So, yes.
I understand her question. Maybe I want to ask it too. She just want to develop a picture about how the operator differs from the Schrodinger picture in the interaction picture.
Okay. So if I again look at the specification. This, and then you can really work out Heisenberg equation motion for the zero order Hamiltonian. We looked at this already. And you can even solve this, namely that x of t in the interaction picture is given by this. As a solution to this Heisenberg equation motion. So you know exactly how to solve the problem. Once you're given initial condition on these operators, you can work out what the operators are at some later time, according to time evolution by H naught. But you may apply some interaction to this, I don't know, x to the fourth. Then what used to be in this ground state may start to hop into some other states due to this perturbation of the system. Operators still follow this a solution to the Heisenberg equation motion, but state can now change. What used to be in a ground state get perturbed by this perturbation, then you might find a particle to jump to some excited state. So states change as a function of time due to this time evolution operator, which is purely due to perturbation. If you switch off this perturbation, the ground state stays in the ground state forever. But once you turn on this perturbation, you might see states hopping from one to another, and that is what is described by this time evolution operator in the interaction picture. And because they've already taken care of the time evolution due to the unperturbed Hamiltonian, the impact you're looking at is really due to the perturbation alone, and that's the problem we're interested in. Does this make it a bit more intuitive?
Yes.
Perhaps I can rephrase her question into this. What we familiar is the operator and states.
Oh wow! So you're
Yeah.
Einstein's equation,
Yeah.
general relativity.
Yeah. And
Okay, we're competing with the teacher and Facebook app. All right.
What we familiar is the states and operators in Schrödinger picture, right? Now we want to know how do you understand the operator in the interaction picture based on the Schrödinger picture. Is that?
Yeah. If you look at the Schrödinger picture, then the states evolve according to the full Hamiltonian. But what H naught piece of the Hamiltonian does is to just give you a phase according to the energy eigenvalue of the unperturbed Hamiltonian. And this phase, in some sense, is not very interesting because you have solved the problem already. You know what E naught is. So we're not interested in that. So when you talk about time evolution in the interaction picture, you are basically removing this quote-unquote trivial phase, which keeps all the states in the states they are. So once you remove this phase, nothing changes as a function of time. What used to be in the ground state stays in the ground state forever. But what you are interested in is the impact of the perturbation that will let one eigenstate of H naught to change to another eigenstate of H naught. So that's what you're interested in trying to capture in this time evolution operator UI. So you're sort of removing trivial part of the problem. Of course, this was not trivial before you started 137, but now you know how to solve the hydrogen atom harmonic oscillator. Has become trivial by now. So you're removing this trivial part of the problem and would like to focus on non-trivial part of the problem due to the perturbation theory. And so that's the idea of this time evolution operator, the interaction picture relative to what you do in the Schrödinger picture. But thanks for the question. So the way I try to explain it here is the understanding of the interaction picture relative to the Heisenberg picture. That's the way I explained it. But thanks to your question, I now explain how the interaction picture differs from the Schrödinger picture. And as I said, the idea is to remove this trivial problem, but rather focus on UI, which is the non-trivial problem. Trivial. Okay.
Yes. So I now have a clear picture.
Clear picture on pictures.
Yes. So I'm thinking, because when we talk about operators, we talk about measurements. But now we are talking about the operators which pushes the states to move if we consider the Schrödinger picture. But now, since both are time dependent, and okay. So now does it mean that always the unitary, the UI, the UI is always, the perturbation always comes with time. So because perturbation might not always be time dependent, but now we always stick them together.
Yeah,
Yeah, that was my question before.
Yeah, so let's move to the discussion of what UI actually looks like. Then you see explicitly what way the time evolution actually is. So as Alessandra asked already earlier, so once we can express this time evolution operator in power series in delta H, then you see what exactly we mean by time evolution operator. So hopefully that answers many of the questions. So what we want to do is expand ui which is given by this expression in part C of delta H. Then it turns out by taking time derivative and then doing time integral gives you the expression you want. Now, of course, if you differentiate it and integrate it, you're supposed to get back the same thing. But if you do it this way, you find a convenient expression that is useful for the power series expansion in delta H. It sounds like a trivial thing to do, but you see how that actually works. So let's take time derivative of this time evolution operator. So time dependence is in the exponent here. So let me pull that out from the exponent. So I h naught t over h bar, here's h naught, I over h bar times I h bar cancels, then I times I is -1. So that's the first piece. When time derivative is this one here, I pull out h from the exponent. This time there's no minus sign because here you have minus I, you have I, so they cancel to 1. So that's what you get. But if you combine these two terms together, you find h minus h naught, that's nothing but delta h. So by taking derivative in time, you now find the expression that manifestly goes to 0 when perturbation is turned off. So what you see that already, you have some power series expansion in delta H going on. And to be able to work it out, we further rewrite it in the following way. So what I inserted is the unitary operator and its conjugate. So by definition, this is 1. So I haven't changed anything from this line to that one. I just inserted 1. But by doing so, you can identify this piece. It's nothing but ui itself. And this piece is now delta H in the interaction picture. So if you go back to definition of operators in the interaction picture, then operators evolve according to H naught.
I think we lost the minus sign there.
Did I?
Yeah.
Yeah. But on the left, right board. Right board. In action, yeah,
Ah, thank you. So this is nothing but the definition of operators in an interaction picture. And this is the time evolution operator itself. So now you have a differential equation for the time evolution operator, which is manifestly only due to the perturbation of the system. Clearly, there is no time evolution operator when perturbation is turned off. And also, this equation is linear. So you have a ui both sides. This is a linear differential equation. By taking the derivative, you basically get this delta hi. then you can solve the problem. Namely that ui, so this is the part of integrating, formally can be expressed as dt h bar. Yeah, that's right. Just to make sure that I'm doing the correct thing. Yeah, that's right. So now that derivative pulls out this delta h in front of ui, its solution should look something like this. But once again, I'm being a little bit sloppy here because it turns out that delta h at different times may not commute. If you remember what we have done with the harmonic oscillator, so xi cosine omega t plus pi m omega sine omega t. So xi at some time is a linear combination of xi of 0 and pi of 0. But some other time, it's a different linear combination of them. So they may not commute. For example, if you would particularly take xi equals 0, and xi at time 1 over omega pi over 2, then this one, if you insert pi over 2 over omega, cosine of pi over 2 is 0, sine of pi over 2 is 1. So this operator is actually p, and obviously they don't commute. So even though this looks like the solution to the differential equation, I have to be a little bit more careful when I write this exponential. And it turns out the only thing you have to do is to introduce this idea called time-ordered product. But before getting into the definition of time-ordered product, at least I hope you see the big picture here. The only thing we did is to differentiate this in time. Then I got this differential equation. Then I'd like to integrate it to find the solution to the time evolution operator, which is now written with the perturbation alone. And once we have an expression like this one, then I can just keep doing the Taylor expansion in delta H to find the operator ID to compute some process at a given order in perturbation. So the only little trick we have to now finish up is what exactly this time order product is and why this is indeed the solution to the differential equation. And once we are done with that discussion, then we can start applying this time evolution operator to any order perturbation theory you like. And if you're strong enough, you may expand this to 100 power in delta H and work out all the matrix elements at that order perturbation theory and start making projections. So the remaining discussion we need to develop is what exactly is the meaning of this expression. But what I'm trying to make sure here is that, at least roughly speaking, ignoring this issue of the operator ordering, this is the solution to the differential equation. But solving this differential equation and integrating it, you get power series expansion in delta H, and that's the goal. So it's sort of a little roundabout discussion here, but we wanted to separate time evolution of operator according to the zeroth order Hamiltonian. Now we would like to see how states change due to perturbation from initial state to final state. That's all encapsulated in this UI. We would like to express UI in power series expansion in delta H. And it just so happens that taking derivative once and integrating it, you find an expression that is suitable for the power series expansion delta H. And it's given basically the exponential of delta H modulo this caveat about the time of order product. So that's the big picture. Any questions about this? Yes.
Yeah, I have a question about why do we call it time-dependent perturbation theory? I mean, is the Hamiltonian explicitly depend on time t or not?
The Hamiltonian is not, you can deal with the time-dependent Hamiltonian too, but right now I'm ignoring that possibility, so I'm treating Hamiltonian to be time-independent.
So why are we calling it time-dependent?
That's because the states change according to this UI. It's just like what I discussed a few minutes ago. If you have some states in the defined in a zero-order Hamiltonian, and without the perturbation, once you actually put the particle in a given energy eigenstate, it's a stationary state, therefore nothing changes the function of time. And what we are doing here is time dependent in the sense that in the absence of perturbation, this particle stays here, but due to perturbation, it may start to hop. And this is a time dependent process.
I get it.
So that's the part which we call time dependent. It's not that the Hamiltonian is time dependent necessarily, but now the states start to change. What used to be stationary states are no longer stationary because of the perturbation of the system. Okay? That's that one.
We put an integral in the exponent to explicit the dependency of time, right?
Yeah, so this is t0. I should probably put t prime here.
Okay.
And by taking time derivative with respect to t,
Okay.
you hit this upper edge of the integral that evaluates this integrand at the upper edge of the integral, which is delta hi at t.
I
Okay?
just wanted to be sure.
Any other questions at this stage? It's good? All right. Then what is this time order product? So definition is that if you have two operators in the interaction picture, and if you take the product of the two, as I said right here, even the same operator x at different times may not commute. So we have to be careful about ordering between operators. And the idea of time ordering is simply that you order them according to time in such a way that earlier operators are to the right, later operators are to the left. So if T1 is earlier than T2, you switch the order. That's the definition. So definition is very simple. And I always find it a little complicated because earlier is on the right, later is on the left. So you have to keep writing like T1, T2, T3, T4 from the right to left. So it's sort of like a Arabic or Hebrew or something. We normally write from left to right, but you have to write things from right to left. Actually, even Japanese used to be written this way, but we switched at some point. I think Chinese the same way. But anyway, so our usual writing from left to right, you have to switch them around in your mind. You have to keep writing things from the right to left. And the only reason why that is so is because you put initial state here, and you put final state there. So you should bring Dirac. He came up with this bracket notation, right? Somehow he decided that the states are represented by ket, which is on the rightmost entry. And the final state is a bra, which appears at the leftmost entry. So when you think about time evolution, you have to start with initial state ket and go to final state bra. That's why time goes from left, right to left. So the other way around from what we normally do. But now that we are used to this ket bra notation, We have to stick to it, and that's why time ordering is defined this way. So earlier objects are on the right, later objects are on the left. And if you have three of those, obviously you have 3 factorial way of ordering them. If T3 is the earliest moment, T2 in the middle, T1 the latest, again we start with the earlier ones. Next earlier one is the latest one in this order. If T2 and T3 are switched, obviously I need to put operator at the time 2. I'm getting tired of writing I and T, so I simplify the notation now. You would do that. If 1 and 2 are switched, you write 3 first, 1 and 2. And I don't bother writing the 3 other possibilities here. So if you have nth order in operator, you have n factorial ways of ordering them, but the rule is always stick to the time ordering. Earlier operators go to the right, later operators go to the left. You sequentially order these operators according to times where this operator interaction picture is defined. So that's the definition of time ordering. And once you know what the definition is, you know what that expression means, at least. Ui of t is time order product of this exponential d0 dy. Then I start doing Taylor expansion of this exponential. 1. And so far there's no issue about time ordering. And at this point, I have to start worrying about ordering. Both T1 and T2 are integrated from 0 to T by this definition. But now that I have 2 operators in the integrand, by expanding this to the second power, I have to worry about ordering between them. And what this symbol T does is to take care of that. Namely that in this integral, I have T1 and T2, both of them going from 0 to T. So I'm integrating over this square, but I divide the square into 2 triangles. In the lower triangle, T1 is bigger than T2, so this operator is T1, T2. So this HI T1, HI T2 integrated over the square is divided into 2 triangles. When you are in this integration region for the lower triangle, these 2 operators should be ordered this way. But if you're on this upper triangle, T2 is bigger than T1. That means I have to order these operators this way. So that's the meaning of this capital T in front of this exponential. So nothing is unusual here. You just literally do the Taylor series expansion of exponential. But when you see second order and higher terms, where you see product of operators, delta H, sorry, they are all delta H. I forgot, delta delta H. Then I have to be mindful of the ordering between two delta H's at different times because they don't necessarily commute with each other. And then this T takes care of the prescription, namely that when you have this the two-dimensional integral, you would divide that into two triangles according to which time is bigger or later than the other one, and then you just order the operators accordingly. Then if you go to the third order term, then you have these 6 possibilities. And what that means is that now you are doing the integral over this cube of T1, T2, and T3 from 0 to T. And I'm not sure I can do this very well. You divide this into 2 tetrahedra. So here I have one tetrahedra, here's another one, here's another one, here's another one, that's another one. The last one is sort of hidden behind. So this cube is divided into 6 tetrahedra. And for each tetrahedron, you order this interaction Hamiltonian in a specific order. But this looks a little still complicated, not easy to deal with. So there is actually a way of dividing it. So let's focus on just the rewriting. Focus on the second order piece. Time order product of 2 of them. And by dividing up the square into 2 triangles, I can write it the following way. This is a triangle where T1 is bigger than T2, right? So this is actually this portion of the integration region. In this case, clearly T1 is greater than T2, so ordering is this. But the other piece of the integral, the T2 is later than T1. So this is this triangle. And in this case, because T2 is later than T1, they are ordered this way. And I keep forgetting deltas. So I'm not doing anything unusual, right? But now I have this expression. You notice that they're actually the same thing. Because T1 and T2 are dummy variables for integral, I'm allowed to switch T1 and T2 inside this integral. Then this T2 is now T1, T1 is T2, T2 is T1, T1 is T2. Once I do this, this is exactly the same as that one. So at the end of the day, instead of dividing everything into 2 triangles or 6 tetrahedra, you can just pick one of them. and that automatically cancels 1 over n factorial. So if you go to n-dimensional cube, there are n factorial number of this, I don't know, what is the version of tetrahedron to higher n? I don't know the name. But anyway, you see what I mean, right? So you divide that hypercube into a bunch of these triangular things. There are n factorial of them. But if you write them out each by each, they all turn out to give you the same answer, just a different relabeling among these time variables. So that cancels 1 over n factorial, and you find this kind of expression. So at the end of the day, this time evolution operator now can always be written in the following form, which is the way you actually do actual computations. So this operator starts with 1, minus I, 0 to t, delta h t 1. Then I have two-dimensional integral only on one triangle. And if you go to third order, sorry, I made a mistake here. I pick only one tetrahedron. Clearly, I'm not good at Latin. The tetrahedron is a singular, right? And tetrahedra is the plural, am I right?
Looks correct.
So in this integration, time ordering is to be specified. Therefore, operators are written according to time ordering. Here also. So this is T1 and T2. So at every order, you pick this segment and integration region where time ordering is clear, and integrate interaction Hamiltonian according to the time ordering, and then you don't have any factorial in front. So that's the meaning of this time evolution operator. Now comes the final thing to check. The claim is that this time evolution operator is a solution to this differential equation. And I wrote this out claiming that this is the answer. And I wrote down what the answer should be, but I have not shown to you yet why this is indeed the solution to this differential equation. And that's the last thing. Once I show that to you, then you know that this is what you can use. And that's actually very easy. So what we would like to show, time evolution of this operator is linear, like this. And I claim this is the solution. And let's verify that. And that can be done at order by order in perturbation theory. If I take the derivative of the first one, time derivative of 1 is 0. So this is 0. And this is order delta h to 0 power. And right hand side, that's always the first power in delta h. So this is at least first order. There's no 0th order term. That's indeed 0. That's kind of trivial. Now at the first order, I have this one. Right hand side, as this one, and then need to do this time derivative. So time derivative is this t that cancels this integral. And integrand is evaluated at the upper edge times IH bar. They all cancel. So the left-hand side is delta HI of t. Right-hand side, I have delta HI of t. We are dealing with UI in power series expansion delta H. We are now looking at first order piece in it. This is already first order. Then I should take the zeroth order UI, which is 1. Therefore, this is satisfied. Looking at the second order in expansion, we looked at this piece here. Then we do t derivative. That would cancel this integral. Then t1 is evaluated at upper edge. So t1 becomes t. And what I get is IH bar minus I squared over H bar squared. And this is actually, the remaining thing is only t2 integral. And t1 becomes t. So this is t. Delta hi t. Delta hi t2. This is the left hand side. Right hand side is the delta hi t. And this is the first order. We need second order. I need to keep the first order piece in ui, which is given by that expression over there. Now comparing both sides of the equation, IH bar minus I squared over H bar squared, that cancels 1 part of minus I, 1 part of H. That matches minus I over H bar. Delta H of t looks like it's inside this integral, but it doesn't depend on integration variable t2. I can take this out of the integral. So that is delta hi of t. The remaining piece is an integral from 0 to t of delta hi. In this case, integration variable is t2, but that's again dummy variable. I can change that to t1. That's exactly this. So you see they match up. Check. Then you can keep doing it. Basically, what we have in nth order is this thing. And when you take the derivative on the left-hand side, derivative is this t. So this integral goes. t1 becomes t. Then you can take this hi of t up front because you don't have any integrals anymore on this variable. And that is exactly the same thing as this side, where delta h of t multiplies ui at 1 order lower, which is precisely the rest of the integral, now that you move this delta h up front. So you can see that this equation, differential equation, is satisfied at each order in power series expansion in delta h. So, at the end of the day, the only thing you need to remember is this expression. And this expression is called Dyson formula. So when you want to understand time evolution in the interaction picture due to perturbation, then you remember just this expression here. It's a simple exponential where interaction Hamiltonian is integrated from 0 to t, and you just take this symbol t in front of it. But now you know the meaning of this t as a time order product, then you know exactly what is this, which is given by this. Then you stick in these expressions are given on the perturbation theory between the initial state you like, which just is here, and the final state you like, which is over there, and evaluate this matrix element, do the time integrals, then comes out the transition amplitude. And it turns out that the Fermi's golden rule we have is nothing but the first term in this expansion. And I'd like to rederive that using this expression in a moment. But any questions about this? So what I demonstrated to you is that I did sort of sloppy discussion that this differential equation can be integrated with this, except of the caveat that you have to make it time order product. Now I define what time order product is. And according to the definition, it should be written like this in power series and delta H. Then we verify that this expression indeed does satisfy the differential equation you wanted to solve. Therefore, that's the solution. Okay? Any questions about this? Everything okay? All right, so let me just then finish up just by focusing on the first order term of this expression and see that this indeed does reproduce Fermi's golden rule. Namely that you have initial state going to final state, and we're using the first order in expansion. And by definition, this delta Hi of t is given by a time evolution, I forgot the sign, according to zeroth order Hamiltonian. And because H naught is now acting directly on the initial state, this H naught just pulls out the eigenvalue of the initial state. This H naught is acting directly on this bra. This pulls out the eigenvalue of the final state. Then I have e to the I EMT over H bar F delta H at 0. Initial state minus I EI T over H bar. Then this matrix element no longer depends on the time, so I factor this out. Then I have this integral, 0 to t. And that's a simple integral. But in Fermi's golden rule, you are interested in the long time, the long-term behavior. So if you want to set t to infinity, when you set t to infinity, this thing is integrated over the infinite period of time. Then infinite integral of this oscillating function is delta function. That's the energy conservation. But at the same time, when you think of this delta function making EF and EI equal, then the integrand is 1. So this thing is the same thing as time interval t. So when you send t to infinity, you basically get delta function, but you square this to get the probability. Square of the delta function in diversion doesn't make sense. But once you identify this behavior, the delta function is the same thing as time interval, then I can take the square of this. That is the probability of initial state I going to the final state F. I take absolute value. Then I have twice this integral. So I assign one of the integral to be this delta function. The other part of the integral to be time. And I'm not sure about the factor H bar here. Okay. So, and then what you can define then is the transition rate, which is probability per unit time. Then this t would go to the other side. In the delta function. And that's the Fermi's golden rule, except that I seem to have screwed up one power in each bar. So when you do this integral, then you get 2 pi h bar times delta function. So there was an h bar here. And then canceling this h bar with this h bar squared, you get this one. And that's the Fermi's golden rule. So the idea is that once you have developed this formalism based on Dyson's formula, you can specifically apply that to the first order perturbation theory that reproduces Fermi's golden rule we have used already. But now you're equipped to generalize Fermi's golden rule to higher orders in perturbation theory. Then you can start computing things like how light gets scattered by an atom that is supposed to tell us why the sky is blue, right? So we will learn why the sky is blue after spring break. So that's the what we like to do next. Any questions? Yes?
I get that as t tends to infinity, the integral grows as t. But how do you replace one of them with t and one of them with the delta?
Yeah, so the idea is that when you compute the probability, you always square the amplitude. So I have this integral twice. So I have this integral twice. And if you care for what helps this conjugation, you might want to change the sign of I, but it doesn't matter. And let's say this one goes to 2 pi h bar EF minus EI. Then you know EF and EI must be the same. So you use the fact that there's delta function to let this to 0. Then this is 1, and that becomes t. So that's the idea that now that you have the square of this integral, you use one of the powers to get delta function, and the other power ends up being just time interval. Is that okay?
Yeah, it still seems very mathematically and not rigorous. But
Yeah, this is sort of a quick mathematical trick. If you want to be more rigorous, you can literally do this integral, because that's exponential.
okay.
And you find something that looks like EI minus EM E over H bar. You square this, then you find this function is oscillatory except when it's 0, something like that. Then you set t to infinity, then this peak becomes more and more prominent, and narrower, and the size of peak ends up being proportional to time interval. This is t down here. So that you actually produce a delta function whose normalization grows with time, and hence it ends up being the delta function times time. That's more mathematical rigorous way of proving it. To the extent that we think delta function is mathematically rigorous, but anyway.
I have one more question.
Okay.
I thought from like regular time-dependent perturbation theory, we get that this transition probability is true for small times.
Yeah. it should be very small, but the delta function is goes to infinity. Does this violate the range of the?
That's a fair question actually. So even though I said T is large, it is meant to be large compared to typical energy differences among the states you are interested in. So relative to those, it is large. But it should be small enough, in a sense, that if you put the system in a finite box, let's say 2p state decays to 1s. But if you're in a finite box, that photon would eventually come back and start causing interaction with the atom again. So you don't want to wait that long. So you have to wait long enough time that photon has to be totally emitted so that you can observe it, which means the time is bigger than typical energy differences. But it shouldn't be too long, so that state would come back to interact with its own. So that's the actually intermediate range of time where this treatment is justified. And if you actually wait too long, what you think is the exponential decay law doesn't go exponential anymore, it starts behaving like power law. But that's when, way beyond the lifetime of the system, so that's where you typically don't observe things. So normally we don't care about that behavior. Okay?
But there is
You look
some-
puzzled. Maybe we should talk
Yeah.
offline. And one announcement, so you guys requested to have the correct homework due next Friday, which is totally fine with me. But I do post the new homework probably tomorrow, that you can stagger them. So if you want to start working on a new one early, you can start doing so during spring break, but it's due in 2 weeks. And the current one is due in a week from now, so you can have 2 homeworks actually in your hand, but you can then control your time how to work on them. So I think that's easier for you. And second, during the spring break, I have to travel to Japan because my stepmom actually has a terminal cancer, unfortunately, so I better see her. And I'll come back in 10 days. So on the first class after spring break on Wednesday, I will be teaching over Zoom from Japan. And I hope that will work fine. And on Friday, I will be back physically, so we get back to one in-person teaching. But just remember on Wednesday, it will be on Zoom with the original Zoom link when we started the semester. Okay? All right, so have a good spring break.